Welcome back. I hope you had a good weekend. Um, what I'm going to be doing here, we're going to be doing a tag team lecture between Professor Adhikari and I. Um, I'm going to be continuing from Friday to talk about iteration and random simulation. And then I'll switch over to Professor Adhikari to start talking about probability and chance. So a few announcements before I get started. Don't forget, project 1 is due this Friday, and we will have a project party this afternoon, 3 to 5 p.m. in 145 Moffett, location where office hours are. What's a project party, you ask? If you want to show up and have a space where a whole bunch of folks are working on the project, come join us. We'll have teaching assistants available to answer questions. You can hang out. You can sit together with other students who are also working on the project. So you can come in person today at 3 to 5 p.m. We'll also have online office hours and project party tonight, 7 to 9 p.m. for those of you who want a remote version. Yes, there are office hours. So this is together with office hours. This is sort of in addition to or together with office hours. Okay, so there's two things that I wanted you to get out of Friday's lecture and what I'm about to show you. The first thing is I want you to know how to use control statements in Python. I want you to know how to use if statements and for statements. And the other most important thing that I want you to learn about is I want to teach you about how to simulate, we call it a random experiment, simulate something happening that involves some randomness using Python code. Okay, so brief refresher on for loops. A for loop looks like what's shown on the slide here. That's how you write the code. If you have an array, the for loop will let you do some operation many times, once for each item in the array. So if you have some code that looks like this, for item in some array, print item. Let me just walk you through the anatomy of this. The item there is a variable name. That's the name. That's a name. And Python will repeatedly make an assignment to that name of the next thing in the array, and then execute the body of the for loop. The part after the in is the array that we're iterating over. We're going to do something once for each element of that array. The body of the loop is the stuff underneath the for. Notice that starts with indentation. That helps Python tell which statements should be repeated. And that code will be evaluated once for each iteration of the loop. In other words, once for each element of the array. Okay, so let me show you an example. Question, how is this different from apply? Very similar. They're closely related. Yeah. Apply also lets you do something for each element in a column of a table. And the something is specified as a function. A for loop lets you do something for each element of an array, and the something that you do is specified by code underneath the word for. In other words, it's the code that's in the body of this for loop. But yeah, good connection that you drew there. Okay, so let's see a for statement. I have here a for statement for I in make array 35711 print I. What is this going to display on in the notebook when I run this code? Nothing. 35711. Yeah, it's going to display 4 lines because it's going to run the print statement 4 times. There's 4 items in this array, and the for loop will first assign the name A to 3 and then run this code, and then assign the name I to 5 and then run this code, and then assign the name I to 7 and run this code, and then assign the name I to 11 and then run this code. Okay. Suppose that I wanted to print hi data 8 folks, but I wanted to print it 20 times because I'm super enthusiastic this morning. If I had an array, I could use a for loop, but there's no array hanging out here. How could I print that 20 times? All right. I like the idea. 20 times print hi data 8 folks. No go. It gave me an error message. So that doesn't work. The times you could use with strings, but you can't use it with like statements or with code. Right. So a for loop would be a reasonable way to do this. So if I want to write a for loop, help if I got the code right. I have for and then some variable name. I'll call it I, and then in, and then an array, and then a colon. Well, I don't have an array, but if I had an array that had 20 elements in it, then I could iterate over that array and do this print statement once for each item in that array. So what I'm going to do is I'm going to create an array with 20 items in it. Now, one way to do that would be to start typing until I get to 20, and my fingers are tired already. And there's a quicker way to do that. So there's a better way to do that. Instead of typing all the items in the array, I can use np.arange, and that will make me an array with all the numbers 0, 1, 2, 3 up to 20. Okay. So if you want to repeat something many times, you can use a for loop, create an array with the right length, iterate over that array, and do that something once for each item in the array. Good question. Good question. Could I do print 20 times data 8 folks? I could. And you can see there, it's printing a string with this concatenation. It's not doing the print 20 times. So I didn't get any new ones. So it does something a little different. So what is the I for? This is a little funky. You notice here is a name, and it never gets used in this code that I'm running. The I here is just a name. I could have used any other name. For instance, this could have been item. It's arbitrary. It's a name that's going to get assigned to each element of the array one at a time. You can use any name you want. I recommend using a descriptive name that describes what that thing is. But sometimes it's handy to save us a little bit of typing and write something very short if it's kind of obvious what it is. And a common thing to use is I or J if you need just a one letter name. Can you reuse it? Yep. This name I sort of only relevant within the body of the for loop. Okay, so let's do simulation. I want to continue from where we were last time. We're looking at how to simulate this very simple betting game where we each roll a die, and whoever die comes up larger gets $1 from the other person. And remember, we wrote some code last time to simulate one round of this game. Okay, so as a reminder, the one round function takes two arguments, what I rolled and what you rolled, and returns the amount of profit that I got. I know it's a little bit egocentric. It's about me, but that's what this function is returning. It's returning my profit. So like +1 if I won $1 and -1 if I lost $1. And then the simulate one round function is randomly rolling my die, or simulating me randomly rolling a die, and it's simulating you randomly rolling a die, and then it's computing my profit. So it's using this np.random.choice to simulate me randomly rolling a die. In other words, getting a random number from 1 to 6. Okay, so now I want to look at what would happen if you and I played this game a bunch of times. A common idiom that we're going to see when we do these simulations, when we repeat this many times, is that we're going to collect the results in an array. So let's say we do it 3 times. We're going to have an array with 3 items that indicate the results from the first, the second, and the third time. So here's a way that we could construct that array. We could create an empty array, make array with no arguments, creates an empty array. And then we could simulate one round of this game and append it to the array. Oh, good. Okay. I forgot some code here. Debugging on the fly here. Hopefully I get this right. All right, let's see what's in the array. The array has 1 item indicating the result of this one random simulation of you and I playing the game once. So let's play the game again. We can execute this same line of code. What we're going to do is simulate the game another time and then append that to the array. Now let's look in the array. We can see here, again, we tied. And there we did it simulate a 3rd time. And now the array shows that we tied the first 2 times. And then the 3rd time I lost $1. Okay, so common idiom, create an array, append the results of what happens in each iteration onto the array. Now you can see that I was doing this by copy pasting code. If I wanted to do it 3 times, I wrote the code and I copy pasted until I had three of these. And if I wanted to do it 5 times, I'd have to copy paste a little bit more. But I said previously I wanted to do it 10,000 times, and I don't want to copy paste 10,000 times. So anytime you find yourself doing the same thing over and over again, you might want to think either use arrays methods or use a for loop. So in this case, we're going to use a for loop. So I want to show you now how to repeat this many times. I want to simulate what happens if you and I were to play the game 10,000 times. I mean, we'd be exhausted, but apart from that, what would the results be? And as before, we're going to collect the results from each time we play into an array. So we want to create an array that has the results of all 10,000 times we played. All right, so we could do this with a for loop. I want to simulate this 10,000 times. So if I want to do something 10,000 times, how do I use a for loop? What should I put? For something, maybe I in something, I'm going to need an array. What array should I use if I want to do something 10,000 times? Yeah, same as before, we saw before. Create an array that has 10,000 items, and then we can do something once for each item in the array. How can I create an array that has 10,000 things in it? Well, I could use np.arange, and that will give me an array that has the numbers 0, 1, 2, 3, 4, 5 up to 9,999. So you see the exact contents of the array somehow is not that important. It's just I wanted an array that had 10,000 items in it. So this is kind of a funny use of a for loop, but it's a very common idiom to repeat something over and over again. All right, and then now we're going to follow the recipe that I was showing you before. We have this an array, game outcomes. In my first line, I make it to be an empty array. And then in each iteration of the loop, I'm going to add another result to the array. So how do I get the result of one playing this game with you once? Simulate one round. Give me that. Okay, so in each iteration of this loop, what we're doing is we're adding one item to the end of the array, like making a copy of the array, adding one result to the end of that array, and then assigning that to the name game outcomes. So when we finished all of this code, we finished doing that 10,000 times, the array game outcomes should now have 10,000 items in it, once for each time we played the game, and it'll have 1, 0, or -1 according to how much profit I got when we played that time. So let's do it and let's look at the array. All right, this is an array that was so long that it spared me from having to look at all the items. But you can see in this simulation, I lost $1 the first time, then we tied, then I won $1, and so on and so forth. And finally, in the last 10,000th iteration, we tied. Okay. So we have an array with 10,000 elements in it, indicating what would happen if we, well, a simulation of what might happen if we played 10,000 times. So that's cool. This is much faster than you and I sitting down and doing this all day. Now we might want to visualize this. So let's put this in a table. And let's look at the table. So here it all is in a table. Now 1 row per time we played the game. Then I'm going to visualize this data by just grouping it to count how many times I won, how many times I lost, how many times we tied. And there it is. There's a count. You can see that I won 4,163 times in this simulation, and I lost 4,122 times. So I won a little more than I lost. And maybe it's easier to look at this as a bar chart instead of as a tabular numbers. And then here you can see a bar chart showing how many times I won. And this bar is a teeny bit longer. I won a little bit, few more times than I lost. So in this simulation, I won a few dollars off you. Yeah, you can pay up after class. There's no rush. I accept checks. Okay, so this is the recipe for doing a simulation. When we do something many times, we create an empty array. We do a for loop to repeatedly do the process, and in each iteration of the for loop, we simulate whatever's happening, the random stuff that's happening, and then we append the result of that to the array. Here, check my bounce. No worries, I'll autograph it, put it up on the wall. Okay, so let's do another example of this. Before I do another example, you notice I used a for loop. I said anytime you're doing something many times, you could imagine how to do it either with a for loop or with array operations. So if you wanted to take a moment to think about a more challenging version of this, you could think about how to do this simulation without using any for loops, instead using array operations. If you're bored between this class and next class, you can think about how to do that. I want to do one more example of a simulation. This time, instead of simulating a betting game, I'm going to simulate tossing a coin 100 times. Okay, so imagine that I have a fair coin and I toss it. It comes up either heads or tails. And I do it 100 times and I count how many times it comes up heads. All right, check to see whether you're with me. What do you think would be like kind of an average number of heads that you might expect if I toss it 100 times? Sure, 50. Absolutely. If it's fair, you'd expect 50% heads and 50% tails, roughly. So if I tossed 100 times, I might get 50 heads and 50 tails. Suppose I tossed it 100 times and I got 100 heads and no tails. What would your reaction be then? It's totally sus, super. Man, it seems really unlikely that would happen with a fair coin. So you'd probably be given the old slant eye, like, okay, Dave, good one, but are you using a two-headed coin or what's going on here? Yeah, so getting 50 out of the 100 to be heads would be totally unremarkable. Getting 100 out of 100 to be heads would be incredibly suspicious. Like that would be an extraordinary coincidence. What about getting 51 out of 100 heads? Suspicious or no big deal? Fine. Yeah, very normal. What about 60 out of 100 heads? Cool. Yeah. Seems cool. Maybe a little unlucky, like lucky for me. All right. So now I want you to just kind of take a guess, think about it a little bit, see what feels. Don't worry too much. Just go with your gut here. Somewhere there's some boundary here, the suspicion threshold, where you're like 50 heads. Okay, fine. Dave got 51 heads. Sure, no big deal. Dave got 60 out of 100 heads. Okay, lucky guy, but believable. 100 heads, you're like, no way. Where's the boundary? What do you think might be a possible boundary? And don't worry about whether it's right or not. We're just trying to take some guesses. Okay, 70, 75, 60. Yeah, anything over 60 you'd be suspicious. Anything over 70 you'd be suspicious. Okay. All right, so let's try to figure out maybe something more quantitative here. Let's try to get some data. So what we're going to do is we're going to simulate this process. Now, if I didn't have a computer and I was really patient, what I could do is I could toss a coin 100 times, write down how many heads I got, do it again, write down how many heads I got, do it again, write down how many heads I got, and just keep doing that for a while until like I'm utterly exhausted and sick of the process, and then look at my piece of paper and see what range of outcomes I got. Maybe one time I got 55 heads, another time I got 42 heads, and then I got 57 heads, and then I got 49 heads, and then I got 40 heads, and so on. And look at those numbers. And if I looked at the range of numbers I was getting, that would give me an idea for what possible number of heads here are plausible, will typically happen with a fair coin, and might give me a feeling for what numbers there are just would be crazy outliers. That would take extraordinary patience, and I'm not a very patient guy. So instead, I'm going to use the computer to do that for me. And we're going to simulate that process so I don't have to write it all down in the array instead of a piece of paper. And then instead of looking at the piece of paper, we're going to look at the array to see what numbers we got. So let's do it. We can randomly toss a coin by making an array with heads and tails. And then we use np.random.choice with this array, and that will give us the result of tossing a fair coin. Well, I said I wanted to do that 100 times. So I'm going to use np.random.choice and pass the second parameter that says, do it 100 times and give me an array. So it's going to give me an array. Let's see what that array looks like. It might look something like this, an array with heads and tails and so on. Now I wanted to count how many were heads. So we can use np.count non-zero. We can use sum. We compare each item in this array to heads. So we get an array of trues and falses, and then we count how many trues there are. All right, so I did this once and I got 50 out of 100 heads, which we said was completely normal. And I'll do it again and I got 57. And I could do it again and I got 49. And I could do it again and I'm getting 45. Okay, so you can start to see here some numbers that might be reasonable. Now let's do it many times. So remember the recipe we're going to follow here. We're going to write some code to simulate one round of this experiment. So in one round, we flip 100 coins and count how many were heads. So I'm going to write a function here to do that. And then we already saw how to do that. So I can just copy paste that code into this function. Boom. Now I have a function that will run around to this experiment. Now I want to, so I said, we're going to do this experiment many times. And I imagined if I was going to do it, I'd do it until I get tired. But computers don't get tired. So I'm going to, maybe it's cruel and unusual punishment, make the computer do this 10,000 times. So how do we do that? We create an empty array to store the results of doing this. And then we do a for loop. My for loop, I said I wanted to do it 10,000 times. So I make a array of size 10,000. And then each iteration of the for loop, I append to the end of this array the results of what happened when I did it once. And the results of doing it once, I can get by calling this function numHeads that I just defined. All right. It would help if I ran this cell. All right, so I'm going to run this cell, and what's going to happen is it's going to run and run and run because it's doing this 10,000 times. So it could take a while. Then we're going to look at what's in this array. Yeah, sorry about the background noise. Folks are working on a neighbor's roof back here. If it gets distracting, let me know and I'll move inside. Okay, so the computer finished running. It was a lot faster than me doing it. And you can see here in the first iteration, 42 out of the 100 simulated coin tosses were heads. And the next one, 45 were. And the next one, 53 were, and so on. So we're going to put this into a table. And then we're going to visualize this as a histogram. And what you can see here is how many heads you might get. And we see the distribution of outcomes for this random experiment. So this is now a fascinating plot. What it shows you is about the most common result is to get about 50 out of the 100 as heads. But sometimes you will see getting 55 heads or 45 heads. You might even see 60 heads or 40 heads. This is fairly rare. It happens only, I don't know, maybe 1% of the time or something like that. And then 65 heads could just barely happen, but it's extraordinarily rare. It might have happened maybe once in these 10,000 experiments. And we never, ever saw as many as 70 heads. Okay, so this now interpretation time gives you a way to set that suspiciousness threshold. If you set a suspiciousness threshold somewhere around like 65, 70, that seems consistent with this distribution to me. If you set your suspiciousness threshold at 55, maybe not a great choice, because a fair number of the times, if it was actually a fair coin, you might get more than 55 heads. And so you might be wrongly suspicious of a coin that is actually fair. Okay. Yeah, we'll say more about the shape of this curve and what it represents. We'll do a whole bunch more of this, but I wanted you to see how to do a simulation and how to do something many times. All right, one more thing I want to show you, a little bit of Python stuff. This is not as important. The most important thing is to know about for loops and to know about simulations. I'm going to show you how to select some of the rows of a table. We previously saw how to use the where operation to select some rows in a table that match some condition. You can also use the where operation to select some rows if you have an array containing trues and falses with one item per row of the table. And then the trues, it'll select the rows where that array has a true, and it won't select the rows where that array has a false. Okay. So let's just see it. Here's an example table with some rows. Each row is an age. And if you wanted to get only the rows that are 18 or above, you could do that with a where clause, with the condition being above or equal to 18. Great, that's what we've seen previously. I'm going to show you another way to get this subset of the rows. I have an array here, ages, that contains the numbers in this table up here. I can do a comparison, compare this array, ages greater than or equal to 18, and that's going to give me a new array of trues and falses. Trues for the items that are larger than or equal to 18, falses for the other ones. Okay, so let's give that array a name. That's that array of trues and falses. I can now use the where operation with this array of trues and falses. And it will select out from the original table only the rows that had a true in this array, which in this case turns out to be only the rows where the age was at least 18. Okay, so this is another way to select rows from the table. Okay, so we previously saw how to do this with the r dot above or equal to 18. That's essentially, it's a conditional thing. It's kind of like a function that returns true or false. So you could either use one of these r dot conditionals, predicates, or you can use an array of Booleans. You can now see how under the covers, the where operation works. What it does is use the apply operator to apply this matching condition to each item in the column of the table to get an array of trues and falses. That's the same array of trues and falses we got before with an array operation. And then it uses where with that array of Booleans. Okay, so you could, multiple ways you could do a where. One way is you could use a predefined condition that we show here. Another way is you could use an array of trues and falses. And a third way is you could define your own function that, given a number, returns true or false according to whether you want to keep it in the output, and then called where with the column and your function. And where we'll call that function on each row of the table, passing in the number in the age column to get a true or a false, and then keep that row if your function returned true. So 3 ways to do it. Why might you use a function? Well, we've given you r dot above or equal to, r dot less than, r dot equals to. So we gave you functions for matching a bunch of common conditions. But if you have a condition that isn't one of the ones that we gave you, no problem. Define a new function and then pass that function, or define an array of bools where the length of that array matches the number of rows in the table, and pass that. All right, 3 ways to do the same thing. You can use whichever is appropriate in your setting. That's all I've got, and I'm going to hand it over to Professor Adhikari now.
Hi, everyone. This is the first lecture we're tagging off, so bear with us if there are a few hiccups. What I'm going to do, looking at the time, we have 15 minutes. What I'm going to do is do another chance simulation. What we're going to get into now is thinking about randomness. You know, what's likely, what's unlikely, how do chances work? And the way we approach chances is to really think of them as something very concrete, to figure out, so that we have sort of visual ways of trying to figure out what chances are instead of relying on formulas. Also, what we'd love to do is develop intuition for you know, how much a certain chance is going to be, or whether it's going to be large or whether it's going to be small. And so we're going to approach chances slightly differently from a traditional treatments. And what I'm going to do today is simply continue with a simulation of a problem that involves chance. When we come back on Wednesday, we'll discuss the rules of chance. And hopefully you will see that very simple rules can lead to quite interesting answers quite quickly. So what I would like to do now is share my screen. And actually run to I'm going to skip over a bunch of slides and run to a simulation at the end. And then when we come back on Wednesday, I will start with the early slides of this lecture. So let me actually find, okay. What I'd like to do is get a sense of your intuition about a well-known problem in probability. And then we'll actually play the game involved and see what happens when we win. And so the Monty Hall problem was a game show called Let's Make a Deal, run by somebody called Monty Hall ages ago. And it was a game that involved chance, and it led to enormous amount of arguing about what, you know, how the results should come out. So let me describe the game to you, and then we can talk for a little bit about how you think the results should come out. Okay, so there was this game show, and at the end of the game, there was a contestant who was faced with 3 closed doors. And the rules of the game were this. It was known that behind 2 of the doors, there were goats, right? So there were 2 goats, one behind each of 2 doors. And behind another door, there was a car. And the contestant's job was to guess which door the car was behind, right? Now, of course, the contestant knows nothing. So if you were the contestant and you were asked to guess which door the car was behind, how would you choose? Yes, it is a very natural thing to go with some random choice. Right, just some random choice of door. Great, so you would pick a door at random. All right, so now what Monty would do is yes, and so as David says, any of the doors holds 33% chance. If you pick at random, then you will get the car with 33% chance. Okay, so Monty gives you, no, there's no other information. Thank you very much. What Monty does is he extends the game a little bit. So you pick a door, say you pick door 1, right? What Monty will do is look behind doors 2 and 3. Now, do you agree that behind at least one of those doors, the 2 that you didn't pick, at least one of them has to have a goat behind it? Yes? Okay. So what he'll do is he'll look at the doors you didn't choose, he'll find a goat and he'll open that door. So you know that that door has a goat. Okay, so now you picked door 1. Monty revealed a goat somewhere, right? And there is another door that is closed. Do you agree still? So now you get to choose as the contestant. Do you ask Monty to open the door that you originally chose, or do you ask him to open the door that remains? And the rule is whatever door you open, whatever's behind it is what you'll get. Now, I must say that there is a certain prejudice here. The car is considered more desirable than the goat. I think goat herders would disagree, but anyway. Yeah, okay, so we're seeing multiple different answers. Let me show you a, so, you know, Monty, there's a couple of doors, you chose one, Monty reveals a goat, and you have to decide. And before we go on to the demo, let me actually see if we can visualize what is going on. This is from the point of view of the contestant. The doors are always closed, right? So when we, supposing randomly we had said, okay, my original choice is door 1, then the car could be behind door 1. Or do you agree that it could be in that circle set? Yes? All right, you told me the chance that it's behind door 1 is 33%. You all agreed with that. Yes or no? Okay, so then what's the chance that it's in the circle set? Two-thirds. The chance has to add up to 100%. Right, so if the chance that it's in my originally picked door is 1/3, then the chance that it's not where I picked is 2/3. So now, one more time. Should you stick with the door that you had, or should you switch? You should switch. You should switch. Because honestly, it doesn't matter what Monty does with the doors as long as your chance, Torin, did your chance, it is still 2/3 in this circled group. Monty might tell you where in the circled group there is a goat, but there's still 2/3 chance that the car is in here. Because if not, if it were 50, then there would have to be 50% chance that the car is behind your original door. But the car never moved. Right, okay, so this, as you see, that there is a tussle, right? Your intuition is saying, wait a minute, we lost a door, now there are only 2 doors, now it should be half. But you can see, if you think about it a little more carefully, it has to be that the chance that it is behind your original door just remains unchanged. That's 1/3. Right? And so you should switch. But, you know, this requires a little bit of solidifying. Anna, I'm not picking a new door. The probability that the car is behind my door, the original one that I picked, is 1/3. The only other place it could be is the other door that is closed. Therefore, the chance that it must be behind that other door has to be 2/3. But I agree. It would be nice to see this in action, right? Shall we just play this game? I think we should just play this game. And so what I'd like you to do is please go to the lecture 14 demo, run the top cell, and then scroll all the way down. I'll do the top on Wednesday. Okay, given that we have limited time, I deliberately kept all the code typed in so you don't have to waste time with my slow typing. Okay, so what we're going to do is we're going to play this game. That is, we're going to simulate this game, and we have to arrange our calculation a little bit. So I make an array of the goats, first goat and second goat. Okay, we have to help Monty display the right goat. So if you pick if you pick the first goat, then Monty is going to reveal the second goat. And if you pick the second goat, then Monty is going to reveal the first goat. And so we define a function called other goat, which takes a goat and returns the other one. And so let's just see if it works. Okay, if the argument is the first goat, it returns the second goat. If the argument is the second goat, it returns the first goat. And if the argument is not a goat, well, then it doesn't do anything. Yes, exactly. It is very, to the people who are saying that there's only 2 doors, it should be 50-50 now. Let me just tell you something. If I asked you, what's the chance that there's going to be an earthquake in the next 10 minutes? Think about this. There is either going to be an earthquake in the next 10 minutes or there is not. Yes, but are you going to say 50-50? Yes, no, or maybe? You're not, because in your head, you are convinced that there is one and there isn't one and not equally likely. Right? So it is still the case that the car is either behind your original door or behind the other door. There are 2 ways, but they are not equally likely. And that's what we're saying here. Okay, so next, let's get an array that says what's hidden behind the doors. There's the first goat, there's the second goat, and there's the car. Okay, and so now we are going to do what we always do. Jayanth, watch. Okay, let me just write a function that simulates one play of this game, right? That's what we've done all along. There is a random event that you are trying to simulate. So you first write a function that simulates one play. Now this game has a bunch of stuff going on. There's what you originally picked. There's what Monty throws out and or what he reveals to you, and then what remains behind the other door. So we were going to return all 3, okay? All right. So every time you play the game, you have all agreed that the contestant picks at random from one of the 3 doors. You agree? All right. So if the contestant guess happens to be a goat, they don't know it. If it happens to be the first goat, then Monty will reveal the second goat. And behind the remaining door, there will be a car. You agree? All right. If the contestant picks the second goat, then Monty will reveal the first goat, and behind the other one, there will be a car. If Monty picks a car, then, if the contestant picks a car, then Monty will reveal one of the 2 goats. We have decided that he'll pick at random, but he doesn't have to. If he liked one of the goats, he can always reveal that one. That's fine. And then what would be revealed would be a goat. And behind the other door, there would be the other goat. Look at these 3. How many times do you see a car in the contestant guess? Once. How many times do you see car in remains behind the other door? 2. Yeah, exactly. Okay. So let's play this game. We're going to play this game. Ooh, I guess the car. Okay, let me just. What am I doing here? I should be running this. Okay. Now, what we're going to do is create a table. I'll come back and do the code later. I'm going to play this game 10,000 times and create a table that has all 10,000 results. And the table will look like this. So I guessed a car, and then the other door had a goat, but sometimes I guess a goat and the other door has a car. Okay, how can we count the number of times I guessed a car? Or how can I count the number of times I guessed each of these? By group, yes. And given that we have 10,000, roughly how many times should I have ended up choosing each of these? Yes, about a third of 10,000. One more zero. Okay, and you can see that in the counts. Now, shall we count what remains behind the other door? Let's count what remains behind the other door. Same way. Haha. Should you switch? Yes. Okay, so here we have joined two tables, and I'll show you the bar chart. Okay, the blue is your original choice. And the gold is what's behind the other door. Daniel, it's section 9.4. Okay, we're out of time. We'll come and talk about this when we start out on Wednesday. Notice that intuition and probability is something that develops. And so we will talk about probabilities in a way that I hope will help you develop your intuition. Okay, so I will stop here and hang around and take some questions. Okay, there was a question that just flew by on the chat. Do you mind posting it on the Q&A so we